Okay, so what we want to be able to do now is that we've been able to find area bounded between two curves. We've been able to integrate from left to right. We've been able to integrate down to up and top to bottom, bottom to top. And I think you guys have hopefully had some pretty good success with this. People had a work day on Friday. Your worksheet is due today. By the end of today, you should hand that into the handed box over there. You guys have a worksheet with 8 problems on it. And a lot of you guys had that done, so that's what I am collecting today. You guys do not have to come to school tomorrow until 3rd hour, correct? Yeah, if you're here by 10:05, you should be just fine. Okay. But, I mean, I definitely have stuff planned for this time. Just know I'll be running from an area which I'll be administering a test and trying to get here, so might be a little haphazard. So what? Nope. Yes. Well, it's like a minute late. Okay. So the question is we've been able to find area bounded between the x-axis and the function. Now what we want to be able to do is we want to be able to take that area. We're going to revolve it around the x-axis. And we're going to find the volume of the shape that is formed. Okay? This is really cool. We are doing basics of volume. There's what? There's going to be some much more difficult type of volume problems. But this is the absolute basics. So, if I were to take this shape and I were to revolve it around the x-axis, I would get some type of 3-dimensional figure. It doesn't necessarily resemble anything that I'm really well aware of, but I could try to draw a little bit of that same figure on the other side. And here's what I'm going to do. Okay, so that's a disc. Okay, if I were to say go to the meat market and I want to buy a ham, if you slice off the end of a ham, you might, depending on what the ham starts and looks like, you might get a disc type shape, right? Now some people like their ham thin, some people like it thick. It doesn't really matter. We just draw one disc of it. And so what I can do now, yep, very good. Yep. Do you get the idea? I'm going to create, instead of an infinite number of rectangles, I'm going to create an infinite number of discs. Now, does anybody know, what did we call the width of a rectangle? Dx. So, the width of one of the slices is dx. Okay? And what we're going to do is we're going to integrate from A to B. But we have to have the area of a circle in this situation. Okay, now we'll get to that in a second, but we're going to integrate a bunch of areas. So the idea is instead of adding up an infinite number of areas of rectangles, we're going to add up an infinite number of volumes of slices. Now those volumes have an, if you look at this first slice I have here, okay, as dx has a certain width, that can be kind of the height of the cylinder, right? And if we want to know the volume, we would find the area of the circle and we would multiply it by the height. So I have the area of the circle is a of x times dx, which is going to be the width or height of the, cylinder. Well, let's just extrapolate this just a little bit further. Now, we're going to use Ben's idea, and we're going to take the area integrated, the volume integrated from A to B, and we're looking at the area of a circle. What is the area of a circle? Pi r squared times dx. What's the problem with writing the formula like that? Right, the radius changes. We have a different, variable here. So let's think of the area in terms of x. The radius. Very good. If you look at this shape right here, this disc that I cut off, would everybody agree that from where I'm pointing right here, from this spot to this spot, would you agree that that's my radius? And would you agree that that's equal to the height of the function? So therefore, and I can't always, this doesn't work all the time. We have a lot of different shapes that come up, but this is one basic formula. We integrate from A to B of pi times f of x quantity squared dx. And this is a disk method. We slice off a disk, we're going to integrate it. Now our bounds of integration change. And our rotation changes. Right now we're revolving around the x-axis. I want you guys to understand that there will come a time we'll revolve around, say, y equals 1. So we'll take this shape and we'll revolve it around there instead, which creates a hole in the middle. We'll take the shape and we'll revolve it around another function, say x minus 3. We'll take the shape and we'll revolve it around the y-axis. We'll take the shape, we'll revolve it around y equals negative 3 or x equals negative 3. So I'm just saying that this is the very basics of our beginning, and we have a good start. We're now ready to go. Let's go to the next page. Yes, without a doubt. The revolution, as it happens, you're viewing it in a three-dimensional space, right? In multivariable calculus, we could take just about any type of shape and revolve it in a fourth, fifth, sixth dimension, whatever you would like to do. Question. You need to visualize it. Yes. I have some good visuals I can provide too. Yes. Are you done? Okay, find the volume of the area bounded by y equals x squared and y equals square root of x revolved around the x-axis. We don't want to do this yet, okay? We're not quite ready for this, okay? We're just going to find the volume of the area bounded by y equals x squared, the x-axis, and x equals 3. And we're going to revolve it around the x-axis. That's where we're going to start. I first start by drawing my region that I'm rotating. Yep. So I'm going to draw my shape. What does x squared look like? It's a parabola. Heads up like that. It's bounded by the x-axis. It's bounded by x equals 3. And so what I'm going to do is I'm going to take that region right here, and I'm going to rotate it around the x-axis. And if I do that, I will end up with everybody agree that that's kind of the shape you get? What would you call that shape? Sure, funnel. It's almost like, for anybody is in band, like the end of a trumpet, or those coin things that you drop around. Yeah. Yes, it is like the throat of a black hole. Yep. It looks like a parabola rotated around the x-axis. Yes, very good. So what I need to do in this situation is I'll set up my integral. And what I want to do is I want to take that slice I just cut. And I know right now it seems obvious, but we're going to cut different things out. Sometimes we're going to cut a cylinder out. Right now we just cut a disc out. So I'm going to draw my disc. So I cut a disc off. So what we're doing again is we're adding up an infinite number of discs. So what I need to do is I need to express the volume of that disc. First of all, what is the width? Good. This is dx. Would you agree that that red line represents the radius? Radius is equal to? X squared. If I were to take, watch again, I'll use a blue marker. If I were to start here and I were to cut off a section in the middle of this, okay, if I were to cut off, say, a section right here, you could see that the height, I'm sorry, the radius of that disk that I just cut off is the same as the height of the function, which is f of x, or x squared. Okay? So, we go to work. What is the area of this circle? Good. If I want to figure out the volume of it, I still have to multiply it by its width, which is dx. So I can take that piece and integrate it from 0 to, good. I can take the pi and move it. Do you agree? What's 3 to the 5th? Yep. I don't know. I'm not understanding. Yes. 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 Okay. I think you guys are ready to try one on your own. Okay. Here's I have another one for you then. Okay, so I'll help you draw the area just because sometimes it's hard to make sure we did it correctly. On the last one, I should have written y equals 0 as well. X equals 0. That just means the first quadrant. Okay. So just get you started. This is the, that's the area that you want to revolve. Okay. We're going to revolve that area, come up with the volume. Go. Oh, it's on freeze. There we go. Okay. All right, let's let's try this. And you guys, everybody's gonna be at different points right now, okay? But we'll all get to the point where the disk method will be very, very simple, okay? So if I take this and I, put the same thing down here, okay, and I take this shape and I spin it, what shape do you get? Sure, half of an egg, half of a football. You get, the point is, though, is that what did I cut off? I cut off what shape? A slice, a disc. So I want to look at what I cut off. I cut this shape off. Okay? It's that shape that we want to work with. And we realize that it has a width of dx, and we want to examine the area of it, so we need to know the radius. The radius is going to be the same as this, right? Which is the height of the function. What is the height of the function at any given point? Square root of x. So now I can plug this in to, pi r squared dx. I get pi times, what's the square root of x squared? Right, so pi x dx is what we will integrate. So we're going to integrate from 0 to 4 of pi x dx. I'm going to move my pi out front. No. So now I end up with pi times x to the second over 2, evaluated from 0 to 4. I plug in 4, and I get 16 over 2, which is 8. Yep, and 0, so you get 8 pi. What we're doing is unbelievable. Yes. Okay, we're ready for something slightly more difficult, okay? So now this is the problem. Okay, we're going to take the area bounded by the first quadrant, y equals 0, x equals 0. Then we're going to go x squared, y, and y equals 1. And we're going to rotate it around the x-axis. Now, this creates a little bit different scenario. Yes? Nope. Maybe, but I don't think so. If I'm understanding it correctly, no. If I'm not understanding correctly, then maybe. But here's what we look like, okay? So if we look at y equals x squared, very different shape here, guys. Y equals x squared. And we are going to have y equals 1. And again, we're bounded by x equals 0 and y equals 0. So this is the shaded region, right here. Everybody agree? That's the region I want to rotate. So if I take this and rotate this around, I end up with like an anti-cone. Sure. You guys, I'm gonna erase this and draw it one more time, okay? All right. I'm gonna draw it one more time so you can see again what's happening here. If I take this, okay. Watch. Question. Okay. So this is the region that I want to revolve around. Watch what happens if I slice it, okay? I'm just going to slice it by drawing a line this time and draw my new shape over there. If I take any part and slice it, obviously I'm going to come up with a circle as I rotate it, right? But Yeah, exactly. Not a donut so much as a washer, right? So that's what I have. I have this shape right here. If I were to cut it, this is the shape I get. That's the shape I get. Because you have, so the area I'm going to cover in black, that's solid area that you are going to rotate and integrate. But the area in green, that's empty space. Right? So if you were to cut that, you would get a washer type shape. Question. That's what we're going to do. So if I want to be able to identify the area of a washer, what do? You remember the area of a washer? Here's the area of a washer. If you want to be able to find the area of a washer, what you need to be able to do is you need to be able to find the big radius and the little radius. You need to subtract the components. Now you can factor a pi out to the outside, but this is our task. Now tomorrow I'm going to give you a worksheet that has some basic volume problems on it. But this is as far as I want to extend today, but I just want you to see that we can create much more difficult. And this is still not very difficult for us. Yes? Yeah, that would be the inside. Exactly. Yes, you can do that without a doubt. For the sake of the fact that you will not do that generally with your problems, I am going to work it out. But that is the most valid method. If you had that on your test, I would be very happy and pleased if you guys did that. Yes. Okay. So, now, watch. I need to identify two parts. I need a big radius, and I need a little radius. Now, look at your shape. Sometimes this is what I do, you guys. This really helped people last year. What is this axis that runs right down the middle there? It's 0, right? Y equals 0. What is this piece that runs across the top the entire way? Y equals 1. What's this piece that runs through the middle? That's x squared. So as I drew that, it seemed like people could kind of understand what is the big radius the entire time, the distance from here to here. 1. It's always 1. Distance from here to here is 1. So my big radius is 1. What's my little radius? Okay, now we're almost there. I can now write it as pi times the integral, and we'll define our bounds in a second. We have our big radius squared, which is 1, minus our little radius squared would be x to the 4th, and we attach our dx because that's the width of the entire washer. Now let's talk about our bounds of integration. We know that we start at 0 in this situation, but what is this intersection point? Where y equals 1 and y equals x squared meet. Where does 1 equal x squared? For x equals 1, so 1. So sometimes you have to do a little algebra to figure those pieces out. So now we have this piece, and now we integrate. What is the antiderivative of 1? Good. So we have x minus, what's the antiderivative of x to the 4th? We're going to evaluate that from 1 to 0. If we plug in 1, we get pi times 1 minus 1/5, which is 4 pi over 5. Yeah, and we're just gonna pause right there, and we'll pick this back up tomorrow, and you guys will try some problems. But you can see that this is pretty incredible what we're doing with slicing these pieces and then finding volume. Derek? Okay. I'll try to find a YouTube video to show you guys. No assignment tonight. I'll give you time to work tomorrow. All right, birthday tomorrow. Be ready.